Is everybody bored yet? This is part 4 of the RTL SDR video series, and I would really like to try a square wave to drive the local oscillator port of the mixer. This kind of seems awkwardly reverse since we've taken great pains to filter the sine wave and to try to reduce harmonic content before introducing it to the mixer. Now we're going to put this square wave in there. Let's see what happens. Also, it might be time to talk about what a mixer is and why a mixer does what it does. And I'm not going to do this in a complicated Taylor series mathematical proof. We're going to use some practical examples to try to unwrap what is one of the more difficult things to grasp or understand in radio, and that is how mixers actually work. Finally, we talked about attenuation and introducing attenuation in order to preserve dynamic range with an extremely limited dynamic range unit. We have an 8-bit A to D in our little dongles, and we need to preserve as much dynamic range as possible by limiting the signal going in. So I would like to try some type of attenuator that we can put a knob on and we can turn the gain up and down with the twist of a knob. So we'll try a variable attenuator circuit. So I hope you guys all enjoy this fourth kind of an add-on to the SDR-RTL Upconverter series. Okay, let's talk a little bit about square waves. So I think that filtered sine wave local oscillator that we developed, it's working pretty nicely in the upconverter. You might ask then, why do I want to try a square wave to drive the LO port on the mixer? We took great care to filter out our sine wave local oscillator in the third video. The idea was to remove the harmonics that might produce more intermodulation products and spurs. First, let's look at mixers themselves. What are mixers? Basically, a mixer is a device that performs the task of frequency conversion by multiplying two signals together. In our case, we have the local oscillator signal, and then we have all of the signals in our input band, basically from 2 to 30 megahertz. So it's a multiplication function. Hence we have that X that's in the mixer symbol that everybody recognizes. Now mixers are nonlinear circuits. Every book you read and everything you see on the internet tell you this, that mixers are nonlinear circuits. They rely on nonlinearity. So logically, square law devices and cube law devices and any device that exhibits nonlinearity could be a good choice for a mixer. What's the best kind of nonlinearity? What's the finest nonlinearity you can think of? Here's an example of a nonlinearity. How about turning a lamp on and off? Hey, that's pretty nonlinear, right? It's either off or it's on. So I've got what I think is a fairly appropriate prop to put this small receiver in the AM mode set to 25 megahertz next to this lamp. Now I'm going to turn the lamp on and off. Can you hear how the receiver is picking that up? Think about that for a minute. How can me turning a lamp on and off cause a frequency of 25 megahertz to come into the receiver? If we can understand this, I think we're going to be able to understand how mixers work. Okay, the little lamp demo was kind of crude, but it tells you that when you have a nonlinearity, or a discontinuity, like turning something on and off, you can produce all kinds of interesting frequencies. So it's not a big stretch to believe that you could also introduce a multiplication factor when you put two signals into a discontinuity or two signals into a nonlinear circuit or function. Basically, there's two classes of mixers that we work with in radio. One is the common analog mixer you might be used to, the old vacuum tube or valve mixers, FETs and MOSFETs, single-ended. The old base junction transistor mixer. These are single-ended. They have nonlinear characteristics if they're biased correctly. They can also be biased to be linear, but we're deliberately going to bias them to be nonlinear for our mixer service. So a nonlinear device with a square law behavior is a good choice for analog mixing, or what we call analog mixing. The other type of mixer that you might be familiar with, and this is very popular now, is called the switch mixer. This switching mixer, basically it uses a time-varying process in which the elements of the mixer are switched on and off by the local oscillator. This method is preferred because it creates fewer spurious signals. Well, I'll believe that when I see it. Supposedly it provides higher linearity for the required output signals, and our required output signal is F1 plus F2. We're an upconverter. Even in switching mixers, you need that nonlinear device. For instance, the Schottky diodes, or in some cases, MOSFETs. This is also known as a commutated mixer. You'll hear that term. Let's consider what happens to our sine wave when we drive or commutate mixer diodes. By commutate, I mean we turn on the pairs of diodes in the ring in an alternating fashion to produce multiplication on the input signals. Basically, the phase splitter in our double balanced mixer takes the 1, 0 input, that's a square wave, and turns it into a 1 and a -1. 1 turns on one pair of diodes, -1 turns on the other pair of diodes. Well, fortunately, the diode ring mixer is covered exhaustively in the literature and online, so search out some of the YouTube videos and some of the other information on the diode ring mixer. But let's go. Let's try to take this thing apart just so we understand how the ring mixer works. So remember, we're using the mixer as an upconverter. We're taking our low frequency from 2 to 30 megahertz and we're translating it up to 42 to 70 megahertz. And we have a 40 megahertz local oscillator. So with the LO in the polarity shown, that is the rising edge of a sine or square wave, shown by the red current arrow going up, the two right side diodes D1 and D2 get turned on. Diodes turned on are like closed switches, therefore they simply provide a ground point. On this half of the LO cycle, the two diodes provide a ground for the non-dot side of the T2 balun. The RF input, which is that yellow arrow, is also a rising edge. The positive going RF is multiplied by the LO and seen at the IF port without a polarity change. So T2 is going to translate, it's going to take the RF and the LO, it's going to multiply them together, and a positive times a positive gives you a positive. So we're getting a positive on the IF. Current's flowing out. Next, the LO flips, and it's going to go downward, a falling edge of a sine or square wave. Now D3 and D4 get turned on, and now the top dot side of the T2 balun gets grounded. The multiplication results in a current sink from the IF. So the operation of the mixer can be thought of as a square or sine wave multiplied by the RF signal. The local oscillator basically creates an oscillating RF signal with positive and negative polarities. This is equivalent to multiplying the RF by a square wave going from -1 to +1 at the local oscillator frequency. Some other things of note while we're looking at this thing. T1. Let's say we make T1 as a trifilar transformer with all the windings the same on a toroid. What would the output impedance be? It would basically be a 4-to-1 transformer. You know, considering 3 equivalent windings, we have a 2-to-1 ratio, which will produce a 4-to-1 impedance step up. Now we know those turned on diodes don't represent a perfect 100 ohms each, or 200 ohms, giving us a 1-to-1 SWR. So don't expect to have a very good match on the LO port. It's another reason why we like to put attenuators on these ports. These diodes don't look like anything like 50 ohms, that's for sure. They're pretty complex impedances. T2 is interesting. Let's say it's an identical trifilar wound transformer. In T2, we're only using half of it at a time. So even though it should be a 4-to-1 step up, or step down in this case, it only turns out to be a 1-to-1 the way we're using it. So engineers figured out, well, quite a while ago now, probably 30 or 40 years ago, that applying a square wave LO could improve the intermod performance on mixers. And basically, the faster you get those diodes turned on and off, the less time spent in the diode's linear or transition region. You don't want to be in that transition region because that's where a lot of the external signals can come in and produce intermodulation. Well, we really need intermodulation. These mixers actually work with intermodulation, but it's the intermodulation that gives us the desired F1 minus F2 and F1 plus F2. It's all those other ones that are related to the odd harmonics and the even harmonics of all the signals that come in that we're not interested in. And for our upconverter, we're interested in the second one, the F1 plus F2. So we need to get these diodes turned on very fast if we want a strong mixer. So the next question, does a sine wave represent the best way to turn diodes on and off rapidly? Let's take a look at a sine wave. Some amount of current must flow to get the diodes through their turn-on curve and into saturation. The sine wave takes some time to get there. It's kind of an area under the curve issue and a rise time issue. Now let's compare this to square wave drive. It's pretty obvious that the square wave gets the diodes into saturation faster. So the takeaway is that it's now possible to drive the LO with near square wave signals, even at very high frequencies. At 40 megahertz, our LO, we really would like to have the third harmonic, the fifth harmonic, and the seventh harmonic. At least those three to have a quasi-square wave. So some ways to cheat the system. Have you ever heard of a clipped sine wave? A clipped sine wave is kind of like a square wave. You can see how it reduces the time because it clips off the top and you don't have all of that time to get to the very top of the sine wave. Another way to improve the situation is to do overdriving. If we, instead of in the level 7 mixer, we put in maybe 10 dBm or 12 dBm, that's going to get the diodes into saturation faster because you're not using all the sine wave to get them there. So if we can get a near square wave into that LO, we're going to limit that intermittent period when the mixer diodes are partially open and partially shorted. And that's going to reduce the intermodulation distortion. I know it's kind of hard to see, but here is what happens when two signals are multiplied together. You can kind of see the lower frequency, the F1 minus F2. It's a little harder to see the F1 plus F2, but it's there. This is a fair representation of multiplication that's occurring in the mixer. I want to put a square wave into the mixer, into the passive mixer, as opposed to a sine wave. I'm going to put a very sharp square wave into that mixer. So now I can just unsolder a couple of ground points and this oscillator will pop right off. I will eliminate the filter and we're going to feed a square wave in there. So there's a little bit of circuitry and modification to the experimental board. So I got this tremendous circuit off the internet on a YouTube channel. The IMSAI guy, and of course he's pointing out that this came from W2AEW. I want to build this up. This will be the basis for our square wave driver, and I will modify the circuit so that it'll take the sine wave out of our regular overtone oscillator and square it up, and that's what's going to drive our little mixer. Instead of a sine wave, now we're going to have a square wave. I'm using the 74HC14. It's a high-speed CMOS hex Schmidt trigger inverter. And the nice thing about a Schmidt trigger is it can be used to turn a sine wave into a square wave. So that means that I can use my original 40 megahertz overtone oscillator and simply couple into the input of the first Schmidt trigger on the chip R1, the 100K potentiometer, allows me to control the bias on the Schmidt trigger so that we get a good 50% duty cycle, and that allows you to adjust that duty cycle. Unless we have just about perfect duty cycle, that can also perturb the mixer and you get more spurs and so on. Notice I have 3 capacitors on the positive pin of the chip. We're trying to bypass the chip at low, medium, and high frequencies. Don't be afraid to add even more, and make sure that you bypass pin 14 directly to ground and use a ground plane if possible. You'll notice all the rest of the chips are being fed from the output of that first Schmidt trigger. They're all in parallel, and I've got a bunch of 220 ohm resistors there. And if you divide that by 5, it's approximately 50 or 60 ohms. And that will make a good drive for the LO. I believe we're going to have enough drive. We might even need to attenuate a little bit. But a square wave can be attenuated with no loss in high frequency performance. As long as the attenuator can handle the 5th to the 7th harmonic of the frequency, there's no loss going through an attenuator. Also, high-speed CMOS runs on 5 volts, so there's a small 5-volt regulator required to come off our 12 volts. So the next thing you should be asking is, Mike, how fast is it? I'm driving it with my little Heathkit sine wave oscillator, and I've only got it set for a modest 100 kilohertz. So let's see if we can get the rising edge. I have my scope set as fast as it will go on the regular time base, and I believe that time base goes down to 50 nanoseconds per division. That's as low as it will go. So it's probably beyond the capability of this scope, which is a very modest oscilloscope. It's only a 60 megahertz scope, so we are being limited by the scope. And I was able to borrow a better oscilloscope, one that has a 1 gigahertz bandwidth, and that's kind of what we need. I used one of those TCXOs with a sine wave output temporarily to be my source, and squared it up, and this is what we got. It doesn't look too bad. You can see it's definitely got the third harmonic in there. And as far as amplitude goes, 2.65 volts, 2.5 volts call it, that's going to give us a lot of output, and we really are going to need that 12 dB pad, that's for sure. The rise time, 2.55, probably 2.5 nanoseconds. Not great, but not too bad. The chip isn't quite fast enough to give us a perfect rise time to get up to the 7th harmonic. If we use 0.35 and divide that in, we get the 3rd quite nicely, and we get the 5th probably with enough to be effective. Remember, you don't need full amplitudes at the harmonics. The contribution of the harmonics as you go up those odd harmonics is much less. Just to clear the decks a little bit, I've removed the 40 megahertz oscillator, and we'll put this back on later. Okay, well, the good news is it came right up. We're picking up signals. This is WWV at 15 megahertz. So I am noticing that the CB band is pretty active up here at 26, 27 megahertz. Picking up a 10-meter beacon. Not bad. Here's some PSK 31 on 10 meters. And now I'm going to attempt to get the trap on there to try to get rid of the 40 megahertz. So let's tune the trap a little bit. Going the wrong way. Wow!
At 12000, wind 190 degrees, 18 knots. That's going great anyway. Right now,
so this is 17 meters. So next I would like to try a little bit faster chip. A faster chip in a single package. This is going to be an attempt to get a little better square wave. The little SOT23-5 Schmitt trigger inverter is a package that you do not want to be breadboarding unless you have a proper technique or a board that you can buy that has the actual footprint of the part on it. Otherwise, you have to do some pretty fine carving on the board, and I attempted to do that with a razor knife. I don't know if this is going to be successful. I haven't put power on it yet, but this is my carving job. Boy, I hope you can see that. That is a very small part. I'm looking through my mag light, but right down here, that's it. As you can see, I've piled up a couple of chip caps and a tantalum capacitor on the positive pin, the VCC pin, pin 5. It really needs good bypassing to ground because this thing is hot. It's got a lot of gain. So you can see the potentiometer for the bias control on the front. And I'm coming off the 40 megahertz TCXO module. Of course, we could use my one transistor harmonic oscillator as well, but this was a quick and dirty way of getting a sine wave into the Schmitt trigger. So this is a much simpler circuit. We're just using one inverter. Wow, to say I'm shocked and happy doesn't begin to describe how well this one little 74HC1G14 is doing the job. Just a single gate, So I've replaced a whole hex inverter with one gate, and it's already showing fantastic performance. This is only a 100 megahertz scope, so it's not able to show the full deal, but this is certainly a much better looking square wave. So 586 millivolts peak to peak is the equivalent of about 8 dBm. Not going to touch a thing. 8 dBm drive into that mixer is going to be just fine. So the TCXO that I bought needed 5 ppm of correction. Remember, the homemade oscillator with the crystal required 3 parts per million.
Next time, and all the best, and see you later. Bala, all the best at 73 Kilo India 4 Yankee. Next time, this is XC1 at
Quite a few people chasing this Saudi Arabia station. Now I'm going to use the attenuator. I have the attenuator on minimum now. At these low frequencies, I think we can get away with using ordinary switching diodes as our variable capacitance diodes. Normally this would use pin diodes, which are more effective at microwave frequencies and allow more attenuation because of the way that they're built. The minimum isolation in the network is set by the capacitive reactance, the series reactance of the diodes. The use of 2 diodes in place of 1 increases the maximum attenuation and doubles the upper frequency limit for a given value of attenuation. So the twin diodes which occupy the position of the series resistor are physically set up to be 180 degrees out of phase, resulting in cancellation of even order distortion products. The resulting attenuator network is symmetrical, and the bias network is substantially simplified. You do need enough reverse bias to turn the diodes completely off, and you have a 5-volt standing bias that keeps the diodes on. So you need to overcome that. So I built an emitter follower circuit that simply works as a voltage variable source to act as the volume control or the attenuation control, VC. It's a simple emitter follower off a potentiometer filtered with capacitors. Now I'm bringing the attenuator back up. Okay. So I promised that I would develop a simple attenuator that had a control so we could change the gain. And I found this wonderful circuit, and you have to give credit to a Hewlett-Packard engineer that developed this circuit, but I really didn't know what resistor values to use, so I just took a guess at some of them. I used ordinary 1N4148, 1N914 diodes rather than pin diodes, and it's working wonderfully. Okay, this is CHU Canada. I'm going to adjust the voltage variable attenuator. It's 5 dB steps. So there's about 5, 10, 15, 20, 25, 30, and honest 30 dB of attenuations available with the simple circuit. It does have some loss, there's no doubt about it, but this is a place where we can afford a couple dB of loss. Okay, I think that this has been an exhaustive series on the SDR-RTL Upconverter, but I tried to cover things lightly. I know in this video I got into some mixer theory. If you think you understand mixers, give up now, because I'm not a math guy, and even the math guys at best have models. They talk about, I have a certain model that fits what the mixer does. It's not really a multiplier. It's kind of a multiplier, but it's got all these other terms too, so don't expect that you're going to get a nice crisp answer like I presented, where it's just a strict multiplier. It's much more complicated than that with these nonlinear systems. So I'll put the schematic in high definition and a parts list up on my microwave Facebook page, the radio resource page on Facebook. You guys like to have good schematics you can print out, and that's hard to do on YouTube. But I hope you've enjoyed this series. I hope to do some more tube type circuits in the future. It's time to go back to maybe some simpler and some tube type circuits. I've done this solid state stuff for the last couple of months, and that's getting kind of boring. So let's go back and do some vacuum tube stuff on the next video.